Now let us see something about the nucleophilicity. Nucleophilicity in different types of solvents, taking the halide ions. Let's first see what if a polar protic solvent is used. See, in a polar protic solvent, anions form hydrogen bonds with hydrogen of the OH group of water, right? Now let us see what happens during that. If you consider the halide ions, see the fluoride ion is the smallest, whereas iodide is the largest, right? Now because fluoride ion is the smallest one, it is heavily hydrated. Because we know that the extent of hydrogen or the hydration energy is inversely proportional to size, right? Smallest are heavily hydrated. Now, iodide being the largest halide ion is least hydrated or less hydrated. Now, when this is heavily hydrated, it becomes the largest aqueous ion. Size wise, it will be the largest in aqueous medium. Look at this. Normally the smallest, but once it is taken in a polar protic solvent, it becomes the largest because it is heavily hydrated. Now, normally the largest iodide, since it is less heavily hydrated, it becomes the smallest aqueous ion. Okay. Now, the point is we have to actually see the approachability of the nucleophile. Being the largest, it cannot approach the electron deficient carbon that easily. Being the largest, it cannot approach the electron deficient carbon. I mean, it cannot attack the electron deficient carbon that easily. So, it's a poor nucleophile, right? In polar protic solvents, it is the poor nucleophile. Being the smallest aqueous ion, the I minus can easily approach the carbon which is electron deficient. So this is a better nucleophile. So this is a very interesting point. You have to check the approachability. So because the one that actually donates a pair of electron to an electron deficient carbon is called nucleophile. Now, if that is big size wise, it cannot approach the carbon that easily. If it is smallest, it can easily approach. Okay. Now, the same thing, if at all, is observed in a polar aprotic solvent. Let us see the fate of halide ions. Polar aprotic solvents. No hydrogen is connected, no hydrogen is attached to the highly electronegative atom. Okay. If you observe, solvents like dimethyl sulfoxide, let me give you some examples. Suppose DMSO, dimethyl sulfoxide. Look at the structure. You don't have a hydrogen attached to the highly electronegative oxygen atom. Take DMF. Dimethyl formamide. See, this is your formamide, but when these hydrogens are replaced by methyl groups, you get dimethyl formamide. Even here also, you don't have a hydrogen attached to oxygen. So these are the examples for polar aprotic solvents. Now, when you don't have a hydrogen attached to highly electronegative atom, there is no question of solvation, just as what we have seen in polar protic solvents. You don't have any solvation, no hydrogen bonding. Now again go for the same halide ions. Simple. This is smallest, this is largest. Take them as such because there is no hydration or solvation. Being smallest, fluoride is the better nucleophile because it can easily approach. Now, being largest, iodide is a poor nucleophile. Largest in size. Okay. So the order can be given as this. In the previous case, it was exactly opposite. Iodide was the best nucleophile in polar protic. Here it is the pool. Now let us take another factor called polarizability, based on which again we'll be explaining the nucleophilicity. So what do you mean by polarization? See, the distortion of electron cloud of anion by a cation. Disturbing the electron cloud of anion by a cation is called polarization, right? Let me first show you what that is. Let me take a small cation. Now, when this approaches a large anion, you know the electron cloud of anion is distorted, is disturbed, is attracted towards the cation. Being larger in size, the anion, I mean the nucleus of the anion cannot hold its valence electrons strongly. So the cation, which is small, which has got great attraction over its valence electrons, of course, not only on its valence electrons, but it will now also have attraction over the electrons of the anion. So it can just disturb the electron cloud or distort the electron cloud. So this is the distorted electron cloud of the anion. So a small cation can distort a large anion to a greater extent. This is what I call polarization, right? Power of the cation to polarize the anion is called polarizing power of cation, right? Now, the ability of anion to get polarized by the cation. This is what I call polarizability of anion. Cations have a polarizing power to polarize the anion. Anions get polarized by the cation. They have got this ability called polarizability. Now, see, this is very clear that a large anion is easily polarized. Okay, let me again take the halide ions. And check the polarizability of the halide ions. Take fluoride, chloride, bromide, and iodide. You know, the fluoride is a small anion, whereas iodide is a large anion. As such, the large anions are more polarized these have a more polarizability, whereas the small anions have less polarizability, contrast to the larger ones. They cannot be polarized heavily. Now, these are less polarizable, less disturbing, less distracting. So these have got no problem in approaching the electron deficient carbon. So are better nucleophiles. Whereas this easily gets distorted, disturbed. So is a poor nucleophile. Okay. Now it can be given as this. So in general, it can be given as polarizability is inversely proportional to nucleophilicity. More polarizable, less nucleophilic, and vice versa. This is very important. Now, you know the one that is a less polarizable is actually called a hard base. There is a theory called hard and soft acid base theory, which we come across in ionic equilibrium. Now, this is a soft base. More polarizable, so is a soft base. So, this is about the nucleophilicity, taking polarizability into consideration. Now, one more thing that affects the nucleophilicity is a steric, the most important. Let me give you two examples. So this is methoxide. Then look at this. So this is tertiary butoxide ion. Let us compare these two. Look at what is happening. See, if you consider the basic nature of these two, you know, as a base, methoxide is weaker. I mean, the electron density is less at methoxide ion, whereas the electron density is more at the tertiary butoxide ion. So if you compare the basic natures, methoxide is weaker, tertiary butoxide, see, getting too much of electron density from the 3-methyl groups which are electron releasing. So this is having a greater electron density and it's a stronger base. But now when you compare their nucleophilicities, again, see the approachability. You know, being less sterically hindered, this can easily approach. Whereas this one, being bulky, more sterically hindered, cannot approach the electron deficient carbon that readily or that easily. So approachability is more for methoxide and it is less for this tertiary butoxide. So which one is a better nucleophile? Obviously the methoxide ion can approach electron deficient carbon readily. Being less sterically hindered, it can easily approach, therefore, a better nucleophile. Okay. Whereas this one cannot approach the electron deficient carbon that readily or that easily, being more sterically hindered. So, a weaker nucleophile. Okay, so these are the different factors that approach the that affect the nucleophilicity. So generally, when we discuss something about nucleophilicity, remember considering the approachability of that particular species. If it can easily approach, more nucleophilic. If it cannot approach that readily, less nucleophilic. It has nothing to do with the electron density at the donating atom. No. Check whether it can approach readily or not. Now, coming to the reactivity order. See, reactivity order can be given as 1 degree is more reactive when compared to 2 degree alkyl halide. Generally, we don't consider 3 degree. 3 degree are not considered because they are bulky or large. The nucleophile cannot approach them that easily. And remember here the substrate is bulky. Even though the nucleophile is not that bulkier, it cannot approach a bulky substrate. So 3 degree do not undergo SN2. So in simple terms, we can say 3 degree not suitable for SN2. Primary, we generally don't seriously consider for SN1 because primary carbocations are not that stable. In case of SN1, it is the stability of the carbocation that decides the reactivity order. Right? Here, it is the bulkiness which decides the reactivity order. Okay. Now, coming to stereochemistry, the most important one. Let us take something chiral. So this carbon is chiral because it has 4 different atoms or groups. Let us check the configuration at this chiral center. Come on. First rank, second rank, third rank, then the fourth rank. Now, while going from first to third, see, we are going in an anti-clockwise manner. And with the least priority group bonded by dash, we can simply say that here the configuration is no doubt R. Going in clockwise direction, and the least priority group is with a dash. Take as it is. Now, when this is attacked by a nucleophile, okay, immediately this one goes off. Rate determining step or the slow step will of course get a transition state. Now this is a pentavalent transition state. Now in the next phase, this one simply decomposes. Look at what we get. As I said, this one comes here, and this one, no doubt, comes here. Okay, let us again take ranking. First one, second, third, and then this is fourth. Inversion, I mean, Walden inversion has already occurred. And now, while going from first to third, see, you are going in an anti-clockwise direction with the least priority group bonded by dash. So, here the configuration is no doubt S. So, that is how, you get something which is 100% inverted. 100% inversion product is what we get in SN2. Okay. And see, I can tell you that this is the stereo specific. Why? It is because if we consider like what we have seen here, if we start with R, we end up with S to an extent of 100%. Similarly, if we start with S, 100% of R is what we are getting. So one particular stereoisomer giving rise to another stereoisomer to an extent of 100%. Not just this, if we start with SS1, we end up with a trans. If we start with a trans one, we end up with cis. The most important thing is here there is 100% inversion. No retention product at all. Okay. This is very important. Now the free energy diagram. Just one step. We don't consider the second step wherein the transition state, I mean the pentavalent transition state decomposes to give products. Very simple. Take it this way. Now this is the delta G. You can even say this for representing the transition state which has got double positive charges. Okay.